As we have seen in kinematics of fluid flow, various types of fluid and the equation associated with it. We also have studied what is Lagrangian model as well as the Eulerian model of fluid kinematics. Now, just to see whether a fluid is going to flow or not, we need an equation. That equation is called as continuity equation. Before studying continuity equation, let us start with a few basics of thermodynamics. As you have seen in thermodynamics, there are different types of systems. Now, these systems are classified into broadly three types. First system is called as open system. The second system is called as closed system, and the third system is called as isolated system. Now, what is an open system? An open system is a system in which we can exchange heat as well as, or rather energy as well as matter with the surrounding. So, there is exchange of energy as well as exchange of matter. In this case, in fluid kinematics, we'll consider the exchange of matter as exchange of mass. So in open system, it can exchange rather heat as well as energy, that is energy as well as matter with the surrounding. We'll replace the matter with mass in fluid kinematics. So since change in energy over here won't be equals to 0, means it is exchanging energy with the surrounding. So this won't be equals to 0. Final energy is not equals to the initial energy. Same as the mass also. It can exchange matter or mass with the surrounding. So the change in the matter is not equals to 0. Now, in a closed system, it can still exchange heat with the surrounding or energy with the surrounding, but it cannot exchange matter with the surrounding. So that means final matter is equals to initial matter, or the mass flow rate which was initially in the system is equals to the mass flow rate in the initially in the system is equals to the mass flow rate after the system has undergone any process. Similarly, in isolated system, what happens is it cannot exchange heat as well as it cannot exchange matter with the surrounding. So the initial energy is equals to the final energy and the change in mass is equals to 0. That means it does not exchanges mass with the surrounding. So this is an approach of thermodynamics in which we have learned about open system, closed system and isolated system. Now what is its significance in fluid kinematics? So in fluid kinematics, an open system is called as a control volume system. Control volume system. Now, what is a control volume system? The control volume system is randomly a system in which it can exchange heat or energy with the surrounding, and it can exchange the change in mass with the surrounding, but the change in volume is equals to 0. That means the volume of the system always remains same. Whereas a closed system of thermodynamics in fluid kinematics is called as a control mass system in which it can exchange energy with the surrounding, but it cannot exchange matter with the surrounding or the mass with the surrounding. So that is called as a control mass system. So over here the change in mass is equals to 0, so the mass remains constant, whereas over here the volume remains constant. We can say that if this is the system, then this will be the surrounding and the boundary of the system remains intact. Here mass can flow in or mass can flow out, but the boundary remains intact. That means the volume remains constant. Whereas over here in control mass system, the boundary is flexible. That means over here the boundary can expand as well as contract, but the mass should be constant. There is no such thing as an isolated system in fluid kinematics, but we will be considering control volume as well as control mass system. Now, being understood over here, let us go back to our derivation, in which we have to study what is continuity equation for a rectangular coordinate system. So let us consider over here, supposingly, a pipe in which the fluid is flowing from one end to another end. Now, in this entire pipe during the flow, what we'll consider a control volume. Now, there is a small amount of control volume, which is this is the control volume, which is actually a rectangular in shape. So while flowing from one part to another part in this control volume, there is while flowing from one part to another part, we can experience some change in its physical properties. Let us see what are the changes in the physical properties. So let us study what is continuity equation in rectangular coordinates. Now we know we have taken this as the control volume. So let us consider this control volume and study the equation. So it is continuity equation in rectangular coordinate system. So we'll take this same control volume which we had considered over here in a pipe, and we'll enlarge and give some dimensions along x, y and z directions. So since this is the rectangular coordinate system, since it is rectangular coordinate system, we'll take horizontal axis as x, vertical axis as y, and the axis along the page should be z. Okay, so now let us consider this control volume. So considering this as x-axis, this will be as y-axis, this will be z-axis. Let us name this area as A, B, C, D, E, F, G and H. Now, since fluid is flowing through this control volume, it will flow in all the possible directions, that is x, y as well as z. So let us consider the mass flow rate flowing inside be m dot x along x direction, and the mass flow rate which is leaving along x direction is m dot x plus dx, considering the length along x direction is dx. Now similar to this, the length along y direction be dy, and the mass flow rate which is coming inside the control volume along y direction is m dot y, which is leaving the control volume is m dot y plus dy, considering this length as dy. And at the last, along z direction, it will come from along this axis, so this will be m dot z, considering this will be dz, and which will be leaving will be m dot z plus dz. So we have assumed all the possible mass flow rates along x, y and z direction. Now let us write down law of conservation of mass, that mass can neither be created, it can't let us write down what is conservation of mass. So mass can neither be created nor can be destroyed. That means mass cannot be created or destroyed. The total amount of mass in the universe or this system remains constant, or the universe rather remains constant. So over here the volume is equals to dx into dy into dz, that is the volume of the entire system. So now let us see what is the mass flow rate along x direction and what is the mass flow rate leaving along the x direction. So mass flow rate along x direction. So the mass in is equals to m dot x. Now since the mass flow rate is coming inside the surface, we will consider as m dot x. That will be given as rho into area into velocity along x direction, which is u. Now this area, mind you, this is area of cross section. So calculation for this calculation of mass flow rate, we'll go back to our original diagram for calculation of the area of cross section. So these are the area of cross section over here, which is given as dz into dy. So the area of cross section is equals to dz into dy. Let us substitute over here. So rho into dz into dy into u, that is velocity along x-axis. Now m dot out over here will be equals to m dot out will be given as m dot x plus dx. Now this is the mass flow rate which is leaving the surface. Since it is along x direction, the area of cross section will always remains the same. Now this expansion is actually expansion of Taylor series. So we have studied Taylor series previously, that is f of x plus h is equals to f of x plus f dash of x into h upon 1 factorial plus f double dash of x into x square upon 2 factorial, so on and so forth. This series continues. Over here x is replaced by x it is, and h is replaced by dx, and this is m of x plus dx will be given as m of x plus this will be dou by dou x into m dot of x into dx upon 1 factorial plus dou square by dou x square into m dot x into dx square upon 2 factorial, so on and so forth. This expansion will continue. Now over here, why we are using a partial term over here? Because mass is a function of, or rather mass flow rate is a function of x, y, z and t. X, y, z and t. That means mass changes along x direction, y direction, z direction and along with time. So hence a instead of using a complete derivative, we use a partial differentiation. So over here, the value of dx is very small, that is it almost tends to 0. So the higher values of x are equals to 0. So these higher terms, that is raised to 2, raised to 3, raised to 4 and higher value terms are equals to 0. So due to which, what do we get over here? That are this higher order terms are equals to 0, and the output along x direction will be given as m dot x plus dx will be equals to m dot x plus dou by dou x into m dot of x into dx upon 1 factorial which is 1. Now what we have got over here, we have got n dot in as well as n dot out. Now, according to conservation of mass, what do we get over here? Let us understand this. M dot in minus M dot out is equals to mass which is accumulated. So the mass which is accumulated, that is difference of the mass flow rate between the two parts, that is in minus out. So now we have studied what is m dot in, we have studied what is m dot out. So for x direction, for x direction, m dot in x minus m dot out x will be given as m dot x minus m dot x plus dx. Now this will be given as m dot x minus m dot x minus, which is this value, dou by dou x of m dot x into dx. So these terms will go away. Now what you have got, the change in the mass flow rate along x direction is equals to minus dou by dou x into m dot of x into dx. And what is m dot of x, which we have already seen, that is dou by dou x, that is rho into area of cross section into velocity along x direction. So let us write this as rho into u into dy dz into dx. Now this entire part forms the volume of that entire control volume. So ultimately what do we get over here is m dot x or change in m dot x is equals to minus dou by dou x into rho into u into the volume. So the change in mass flow rate along y direction will be given as m dot y will be equals to minus dou by dou y into rho into velocity along y direction, that is v, and volume. Note that we'll take this as a velocity, that is v, and v cross will take as volume, since there is no confusion between volume and velocity, because velocity in y direction we denote by v. Similarly, the change in mass flow rate along z direction is equals to minus dou by dou z into rho into w into v, that is the volume. And now the net change will be given as m dot m will be equals to, that is minus of dou by dou x of rho u into volume, that is all these things, minus of dou by dou y into rho into v into volume, and minus of, or minus right here, dou by dou z into rho into w into volume. Now since this is a control volume, the volume of this entire system remains constant, hence we will take this term outside, and what we will be left with over here, that is volume. Let us take this as minus volume is equals to dou by dou x of rho into u plus dou by dou y of rho into v plus dou by dou z of rho into w. So this is the entire change in the mass. Now as we have seen earlier also, the change in the mass flow rate depends upon the as we have seen earlier also, the change in the mass flow rate as we have seen earlier also, the change in the mass flow rate is equals to the mass which is accumulated. So let us take that equation which we have studied earlier, that is m dot in minus m dot out is equals to the mass accumulated. So now let us see the right hand side of this equation, in which the mass accumulated term we have to consider. Now, so mass accumulated m dot is equals to, that is rate of change of mass with respect to time. So now mass, we know already, it is a function of x, y, z, which we have considered in m dot in minus m dot out. Now we have to see how it is variable with time. So hence we will use this as dou by dou t of m, which is equals to dou by dou into rho into the volume. So we'll take this as V cross. We know density is mass upon volume, so mass will be volume into the density. So the entire equation, that is m dot in minus m dot out, is equals to the mass accumulated, can be together written as, that is equals to minus of volume is into dou by dou x of u into rho, or rho into u, plus dou by dou y of rho into velocity along y direction, plus dou by dou z into rho into w, which is velocity along z direction, which is equals to the right hand side, which is dou by dou t into rho into the volume. Now over here, what you get over here, in this the volume remains constant, so this will come out of the derivative, and this part will get cancelled. Okay, so if you take this minus sign over here and you take it on the left hand side, what you will be left with, that will be equals to, that is dou by dou x into rho into u, plus dou by dou y into rho into v, plus dou by dou z into rho into w, plus dou by dou t into rho, that is equals to 0. Now this is actually continuity equation in rectangular coordinates, but we'll apply few conditions over here. Now what is the first condition which we are going to apply? That is, it is an incompressible flow. If it is an incompressible flow, density does not changes. That means density remains constant. If density remains constant, that means the final density and the initial density is same, and density is not a function of x, y, z and t. That means this term is going to become 0. This term will be equals to 0, and you can take density outside. So what you will get by using the concept of incompressible flow? Now incompressible flow states that the change in density is equals to 0. That means the density remains constant, the final density is equals to initial density, and density is not a function of all the spatial coordinates, that is space coordinates x, y, z and t, x, y, z and time coordinate system. So now over here, the d rho by dou t, or dou rho by dou t, is equals to 0, and due to this, what equation do we get is this dou by dou x, rho is constant, into u, plus dou by dou y into v, plus dou by dou z into w, is equals to 0. Now since this last term is equals to 0, since density cannot be equals to 0, this entire term will be equals to 0. Hence dou by dou x of u plus dou by dou y of v and plus dou by dou z of w is equals to 0. Now, this is actually a continuity equation for an incompressible fluid flow. But over here, we'll apply a few concepts of mathematics. Now, here we'll apply the concept of vectors which we have studied in applied mathematics, which is, we'll assume, or we know that V, that is capital V, is equals to U I cap V j cap plus W k cap, which we have studied, that is the total velocity is vector sum of, or total velocity is ui cap plus vj cap plus wk cap. And we have already seen in vectors, that is the del operator, which is given as dou by dou x I cap plus dou by dou y j cap plus dou by dou z dou by dou z k cap. Now, over here, you can write this equation, that is dou by dou x of u plus dou by dou y of v plus dou by dou z of w is equals to 0 in the form of a vector form, that is a del operator dot v. So this is a dot product of two operators, that is del dot v is equals to 0. Now, we have seen what is continuity equation. This is in 3 dimension for an incompressible fluid flow. Now, if this is a 2-dimension flow, that means that is dou w by dou z is equals to 0. That means it remains constant, velocity along z direction remains constant. Hence, for 2 dimension, dou by dou x plus dou v by dou y is equals to 0. And for 1-dimensional flow, this is for 2-dimensional and this is for 3-dimensional. For 1-dimensional flow, either of u or v will be equals to 0. So I hope you have understood what is derivation of continuity equation in rectangular coordinates. Thank you.